Manaki or Civil Bro. So today we're going to discuss about shear force and bending moment. So this is a topic which many students, professionals have some doubts on, and maybe they don't understand 100% the lectures which are taught in their colleges, and someone wants to revise, someone wants to prepare that for a competitive exam. So all of that basics I'm going to cover, and then slowly in the next lectures I'm going to take it to the advanced level, so that any question in the competitive exams for the shear force and bending moment diagrams you can attempt and solve very easily. So mainly the main focus will be on the concept and developing interest in the subject. So let's get started. And first of all, we have to learn about what is force. Okay, so force is applied on any body, and suppose you can say that force is an action. Okay, and these the other things which are developed, that is the, you can say this, the shear force, bending moment, axial force, these are the these are called the reactions. Okay, or the internal reactions, to be precise, it is called the internal reactions. Okay, so why this is not a textbook definition, why I'm telling this. Suppose you apply you have a particular body, suppose there is a beam here, I'm drawing a real beam here, and it is fixed, that is fixed beam, and some load is applied, suppose W load is applied, and what happens is the particular beam tries to resist the particular load. So for resisting the load, a certain forces are developed. So these forces are known as the internal forces or the internal reactions. So this internal forces, shear force, bending moment, axial force, are developed in response to an external force. Okay, this is also known as external or applied force. So you can see in the terms of when you design the structure, suppose what we design the structure instead, or manually, or ETABS, Tekla. What we do, first of all, we define the sizes of the members. We define the beam column, we make the beam column plan, suppose, and then suppose we define the beam column plan, and we take the sizes of the column. Suppose we take the column size as 300 into 300, and the beam size as, suppose, 300 into 350. So like this we take the sizes of the beams and columns, and after that we apply certain loads which are called dead loads, live loads, and earthquake loads, wind loads. All these loads we applied, load combinations, and then we find out the we do the structural analysis. In the structural analysis, these components, the shear force, bending moment, axial force, are found out, and if the section which we have assumed initially is passed, then it is okay, and if it is failing or showing any warning, then we increase the section or change the size of the section. So this is all this which is in the practical field, but in the this theoretical field, we really need to understand this, how to find out this, first of all, shear force and bending moment. And when you understand this concept, it is useful for design also. But today the main focus will be on solving numericals for your exams. Okay, so let's get started. So here we all know about your moment. First of all, moment is equals to force into distance. Okay, and in the shear force, the distance will not be there. Okay, but when you have in the moment, then the distance factor will be there. And we are mainly going to find out the shear force and bending moment of beams here. Okay, so now what do you think is a beam? So beam is, first of all, it is a structural element. Okay, like columns, beams, slabs, staircase, this is a structural element, and the forces, structural element, forces which are applied are perpendicular to the member axis. So what does this mean? Let's see. Member axis, this is one definition of beam. There are lots of definitions. This is simple definition. Suppose this is a beam, and all the forces which are acting, these are perpendicular to the member axis. If the member axis is like this, so this is 90 degree, these forces. So these this is one definition. And the second definition is your the third dimension. The third dimension is much more than the other two dimensions. This is also another definition of beam which you can use. So suppose a beam size is here, I am just trying to draw a 3D section here. Suppose beam size here is your 250 into 350, and if you see the length of the particular beam, this one span length is suppose uh, 5 meters, means 5000 in if you consider. So the third dimension of a beam is more than the other two dimensions. The same can be in case of column also, but this is another definition. So there are other definitions as well, but I think you understand now what is a beam now. So we'll skip to that. You can just cover the theory part and see what is your response to that. So first of all, we are going to see a little bit about supports. Okay, we have to know about supports before starting the drawing the shear force and bending moment. Okay, so mainly we are going to cover here in any exam you see, first of all you have the cantilever support. Okay, then you have this simply supported, which is mostly covered in books, but actual scenario you will find this, like practical scenario, you will rarely find any simply supported beam. Mainly you will find fixed and continuous. Okay, then you have this fixed, and then you have this overhang. So I can say that in practical field there will be cantilever and there will be fixed. Overhang is this overhang can also be there, simply support overhang. This is the third, I'll say this is the most common, second most common, and third most common, and fourth, this is very rare. Simply supported beam is very rare, but for the exam point of view, for this numerical point of view, you have to cover that also. Okay, mainly it is very important for the exam point of view. So let's go here and see what are this supports little bit in detail. Okay, so we have these things. Okay, rotation and deflection along x axis, deflection, I'll just deflection along. So if this is x, and the other direction which is perpendicular to the x is this, if I say this is z and this is y. Okay, z axis. So these are the three things which are going to happen in a joint. Okay, I'm talking about a joint here. Three things. So where in a fixed support, which is also denoted like this, there is no rotation. So since there is no rotation, there is moment. Since there is no rotation, means there is resistance to the rotation, then there is a moment. This is a simple concept. And no deflection in either of the axes. Okay, so shear force is also there. Since there is no rotation, moment is there, so there is no deflection, shear force is also there. So now let's move towards a very simple numerical here. So this, let's take a fixed beam. Okay, and here it will be A, and let's apply a point load of 4 kilonewton here, to 4 and 6 kilonewton here, 4 and 6 kilonewton here. Okay, that's very simple. So first of all, okay, I'll just draw this, and before just proceeding, you'll need another thing called the sign convention. Okay, so very briefly I'll just explain the sign convention to you. So there are various sign convention used in various books, but I found it the most usable and most easiest one. So if you can follow this, then it will be easy for you. So first of all, shear force. So nothing is there. So if you're going from left to right or right to left, then this can be used. So if we go from left to right, so if you go from L to R or right to left, if you go from left to right, then you will follow like this, and if you go from right to left, you will follow like this. Okay, so simply we can know that the shear force, if it is acting in this direction from the bottom, then it is positive, and if it is coming in this direction also, then it is also positive, and for the negative it is the opposite simply. So it is like this and like this. Whether you come from the left or whether you come from the right, you should have to go in the one direction, left to right or right to left. So you can go in either of the directions. Bending moment. Now bending moment, here we have the two factors, hogging and sagging. So what is hogging? Hogging is like this, okay, and sagging is like this. So now you can take either one of as positive or one as negative. So now if you take sagging as positive, hogging will be negative. So you can take as hogging negative and sagging positive. So what we'll do, this is the only thing on the sign convention, and remaining there is nothing else. So what you do, if this is a fixed beam, so you see the this particular deflection diagram or influence line diagram, whatever you can assume, you can draw this first. This doesn't have any formula, but you have to draw it by your own experience and common sense. So here you can see there is hogging. Okay, so there will be a negative bending moment, and obviously this all these forces will be taken in the negative for the bending moment. So first of all, let's take the shear force here. So since this is a fixed moment, there is no reactions here. Okay, no reactions have to be determined. So first of all, let's start from the right. So this is 0 obviously, and this is 6. So this is 0 and this is 6. So since we know the sign convention of the shear force is like this, for the shear force SFD, the sign convention is this one. So it is, if you're going from right to left, then it is coming like this, so it is positive, so it is 6 here. Then there is no force up to this much. Okay, so we'll have 6 up to this here as well, and here another force is coming downwards, so downwards is positive here as per this sign convention. So and it will add this 6 as well, so it will be, let's say, 12. 6 plus 6, 12. Then it will go up to this much, and again a downward force is coming, then it will be 12 plus 4, 16, and then it will go like this and like this, so it is positive. So this is the shear force diagram, very simple. And then let's the bending moment diagram. So bending moment diagram, since the this hogging is negative, so we'll take it along the negative direction. So here this is the free end, and the free end, the bending moment is 0, so it will start from here. Okay, so at this point, this particular point, at suppose let's name it A, B, C and D. At this particular point, the shear force, what is it? So it will be 6 into 4. 6 into 4 is 24, and it is negative since it is hogging, so 24. And then let's find out at this particular point, at B point. So at B point, what will happen? This particular force of 6, it will be 6 into 4 plus 4, 8. So this particular thing will be 6 into 8, you can say minus 6 into 8 minus 6 into 4. For this particular force, this will be added 6 into 8 minus 6 into 4. So you should keep a calculator with you for calculating this, and this particular sum will be equals to minus 72. Okay, so this will be 72. And next, the bending moment, if you find out the bending moment at A equals to 6 into minus 6 into the entire one, 2 plus 4 plus 4. So it will be 10, minus 6 into 10 minus 6 into 4 plus 2, that is 6, and minus 4 into 2. So if you do this sum, it will be minus 104. Okay, so this is 104 and this is negative. So this is the basic shear force diagram, and let's find out another one. Here let's do another numerical. Now this time, if you want to just do it, then you can pause the video, do it, and then you can see whether your results which you have done is correct or not. And this numericals you'll find in strength of materials SS Ratan book. All these things are in the example. Okay, so this is A, this is, let's call it, this distance is A, this distance is L, and this is the thing. So now in this particular cantilever beam, we have this to find this shear force diagram. So now this is shear force diagram. Draw the sign convention for your preference. Now the downward force is your positive, so it is positive W, and then there is another upward force here, so it is W minus W. At this point it is 0, and there is no force here. So this is the shear force diagram. Very simple. Let's find out the bending moment for this. So bending moment, so first of all, you can see, you can draw the free body diagram. So this is deflecting like this, so there is hogging here. So since there is hogging here, so since this means the bending moment is negative, so whatever the result comes, it will be in the negative direction. Now, so let's find out the bending moment at these points A, B dash, and B. Okay, so bending moment of B is obviously equals to 0. This is the fixed end, sorry, the free end. In the free end, there is everything in the this rotation is possible, so that is bending moment is 0. And then we have this B dash. So let's find out at B dash, and for the B dash we'll need a convention here. We'll taking this convention, whatever it will move along this direction, it will be positive, and the opposite direction it will be negative. So it is moving this this B dash along this direction, so it is positive W into A. So we'll just do this, B dash equals to W into A. Okay, and then at A, so at A, so first of all let's consider this particular load, this W, so it will be W into L. Okay, so it will be W into L, and then it will be minus why, because this load W is coming in the opposite direction, so W into this particular portion. So what is this particular portion? This is L minus A. Okay, so minus W into L minus A, and if you do this, then only WA will be remaining. Okay, WA. So this is at B dash, it is since there is hogging, it is negative, so it is WA, and here also it is WA, so it will be like this, WA hogging negative. So this is the bending moment diagram for this. So now let's do another one in the numerical for the cantilever. So here we have a cantilever beam. Let's say, let's put this time this at the center. This will be 6, this will be 4. Everything is in a single unit, meter, and this will be your 4 meters again. So this is symmetric, and let's give this, A, B, C and D the names. Okay, so first of all, let's find out the shear force diagram. So for the shear force, you find the shear force at D. We're going from right to left, so shear force at D equals to your 0, and the shear force at C, which you find, it is also 0. And then it starts increasing. Shear force at B, if you find out, it will be, okay, I forgot to give this particular load here. This is 3 kilonewton per meter, okay, UDL. So shear force at B, it will be your 3 into 6, which is equals to 18 kilonewton. Okay, so and this will go on increasing, so this will be there, and then the shear force at A will also be 18 because there is no other load included. So the shear force diagram will be like this. So there is no load up to this point, and from this point to this point it increases to 18. So it will be like this, just to make it properly. Okay, so it will be like this, and then it will be like this. Okay, 18 shear force positive. Then we have the next bending moment. So for the bending moment, let's see the bending moment. And now bending moment at the rate here, D will be 0, at the rate C will be also be 0, and since there is a UDL, it will be the results in the graph will be your this parabolic. Okay, and since this is fixed support, it will be here hogging, and since there is hogging, it is negative, so it will be downward negative. So up to here there is no bending moment. Bending moment at the rate B, let's find out. B, it will be this 3 into 6, that is 18, into the center of this 6, so it is 6 by 2, that is 3. So it is 18 into 3, because since we are finding out at B, so at here 18 into 3, it will be at 54. So it will be 54, and we just find out this is in UDL, so it will be like this. So this is a parabolic. So since whenever there will be a UDL load, so it will be parabolic, it will not be a straight line. And then at the next point, that is at the rate A, let's find out the bending moment. A, it will be your this 18 into, now this is interesting, this will be 4 plus 6 by 2. So 4 plus 6 by 2, that is 4 plus 3, that is 7. So it will be 18 into 7. So if you just calculate this particular sum, you will find out the result. So if you just calculate, it will be 18 into 7, it equals to 126. So it will be 126. Just join this like this, and this will be 126, this will be 54. This is hogging, so this is the negative direction, this is the BMD, and this is the SFD. So this is one for this particular shear force and bending moment. So I'll give you a homework which you can do, and I'll solve this particular numerical in the next lecture. So I'm just giving you last question for the fixed beam. So if you just do this, I think you will be able to solve any numerical for the fixed beams subjected to UDL and the point load. So there are other loads as well, UVL as well, so that will cover later, and couples, so there are there, and 6 kilonewton, and there is a UDL of 2 kilonewton per meter, and this is 4 kilonewton which is acting here. This is A, B, C, D, E and G. Okay, and this will be 2 meters, 2 meter, 3 meter, 3 meter and 4 meter. So this is it, cantilever beam subjected to UDL and some point loads. So find the bending moment and shear force diagram and you can mail it to me in my mail ID, which is always displayed in the bottom of your screen, and or you can just just send the answers in the comment section. And if you just find this video useful, drop a like, and in the next lecture we'll cover the other questions of shear force and bending moment diagram of other kinds of support. So stay tuned, have a good day, bye bye.